Alright, let us look at the attributed graph. So far we have only considered the plain graph, right, plain static graph. Now we will consider static attributed graphs, okay. And let us look at the structural based algorithms, okay. So here we look at two types of algorithms, structure based algorithms and community based algorithms. So in the structure based algorithms, what it does, they basically try to exploit frequent substructures, right, can be motif, can be any subgraph mining techniques and subgraphs patterns to spot deformations in this pattern. Whereas in the community based approach, we look at a community and we look at entities within a community and try to identify those entities which should not fit within the community, okay. We will discuss one such algorithm in the community based outlier detection techniques. So in the structural based algorithm for the attributed graph, so the task is to identify substructures in a graph that are rare structurally, that is connectivity wise as well as attribute wise, okay. So what are the problems that we are solving here? The first problem is the problem of finding unusual substructures in a given graph, and once we identify unusual substructure, the next task is to identify how unique, okay, that substructure is, right. Nodes and edges contains I mean that part would be unique, and that would be non-unique attributes in the sense like if you look at the unusual substructures, possibly attributes are very unique, but there are some attributes for some nodes whose attributes are non-unique, right, and we identify those as outliers, okay. So what people do, people try to identify roughly that what is based substructure, okay. So the based substructures are those that occur frequently in the graph and thus and thus can compress the graph well. Again we are looking at it from a minimum description length point of view, information theoretic point of view, and we will use minimum description length principle that basically trades off between the compression quality and the size of the substructure, right, this compression quality and the size of the substructure are devised as the objective function, right. So this is this famous paper Nobel and Cook. If you want, you can look at this paper. I am not again going into the details because information theory itself, you need to understand this concept separately, that itself requires a quite significant time. So I will not go into that part, rather I will go into those algorithms which are based on the foundations that we have discussed so far, okay. And as I mentioned in problem 1, how to define how to find unusual substructure. So we define a measure that is inversely related to the minimum description length based measure defined for the base substructure and and then we rank substructures accordingly. And then how do we identify the uniqueness or non-uniqueness? So define a measure that penalizes, right, those subgraphs containing few or the best, right, few common or few best substructures, making them more anomalous, okay. I understand this is little bit vague. I am not again going into the details of this part, rather I will look at the second part and go and try to go deeper into this, okay. So so this is for attributed static graph, but we look at community structure, okay. So what is the intuition behind this? The intuition behind these types of algorithms is basically that we try to identify those nodes in a graph, right, also known as community outliers, okay. The attribute values of which deviate significantly from the other members of the specific communities that they belong to, okay. What does it mean? Say think of a smoker, right, in a community of vastly non-smoker basketball players, okay. There is a community of basketball players and most of them are non-smokers, but there is one such or one or two such players who are smokers. So, with respect to this community, these two smoker nodes are outlier nodes. But if you look at the entire graph, there are many such smoker nodes, right, and smokers in general are not outliers, right. So, but if you look at a particular community, for that specific community, those nodes are possibly outliers, okay. So these two algorithms, the first one is CODA, what it does, it is a unified probabilistic model that simultaneously finds communities as well as outliers, right, from a graph. In fact, all the algorithms that we consider, all those algorithms identify communities and outliers side by side. The second one is called, you know, GOUT rank, GOAT rank. So, this is again identify complex anomalies, right, that could be revealed in only a subset of relevant attributes, more apparent in high dimensional feature space due to the curse of dimensionality, okay. So, these are more of an algorithm which do not use graph structure, right, generally in this feature space, okay. So, but we will discuss one such algorithm which considers the graph structure, the attributes of nodes and edges and detects outliers, and this algorithm is called FocusCo. FocusCo is an algorithm which identifies community centric outliers from a static attributed graph, okay. So, let us take an example, okay. Let us say this is the graph and there are two communities. So, this is one community and in this community there are 5 nodes and each node is associated with 4 attributes, okay. The degree, educational degree, it can be college, PhD, etc. The current city or state or country, whatever, New York, etc. Then language, right, mother tongue spoken language, Dutch, English, Greek, etc. And then the current job, right, Google, Microsoft, bank, etc. right. So, in this particular community, if you look at it carefully, right, and if you also say that, hey, in this community I will only look at 2 attributes, okay, I will not look at other attributes because this community is defined by these 2 attributes, okay. So, and what are these attributes? We are considering the first 2 attributes, okay. So, the educational qualification and the current place, okay. So, with respect to these 2 attributes, if you see, all the nodes belong to New York city, right. Most of the nodes have PhD degree except this node, this guy has only college degree, right. So, with respect to this community, and how can I say that this is a community? Look at the structural property, right, they are highly connected, right, they are highly connected. So, this is a community, topological community, and they are also attribute wise similar, right, but this node is outlier with respect to this attribute, okay. So, what is the aim of this algorithm? This algorithm, what it does, it first identifies important attributes, right, measures the weights of attributes, then tries to group nodes into communities depending upon the structural properties, right, and then tries to identify nodes within that community which are very different attribute wise, okay. Structurally it may not be different, but attribute wise it may be different, okay. So, let us look at this algorithm carefully. So, the aim is to find user driven cluster or communities, right, and therefore we aim to identify user driven community outliers, right, in a graph with node attributes. Nodes agree on, right, as I mentioned, we try to identify focus attributes or important attributes, right, we call them focus attributes, and then it finds clusters of densely connected nodes in the graph that also agree on this attribute space called focus clusters. Okay. So, what is the idea? So, idea is that we let us assume that user has already given you that a set of nodes which are similar. Okay. So, what would be your task? Your task would be to identify a cluster where nodes of similar types of the exemplar nodes, right, will be clubbed together, right, and form a cluster. Now, within a cluster you identify focus attributes, okay, the focus attributes which define this cluster, meaning the focus attributes which are unique to this cluster, okay, and then we call this cluster as a focus cluster, right, and an outlier is defined as a node which belongs to the cluster structurally, but deviates from it with respect to the focused attributes. Okay. So, this node belongs to this cluster structurally because this guy is connected to all the other guys, right, but attribute wise it is not that suitable to be placed within this cluster. Okay. All right. So, this is the problem statement. Given a large graph G, V, E, F, V is the set of nodes, E is the set of edges and F is a set of attributes. Remember, each node has a vector of size mod F of attributes, okay, and we are also given a set of exemplar nodes CEX, right. So, this CEX set of nodes are similar, okay, both structurally and attribute wise. And what is the aim? The aim is to infer weights of attributes, okay, beta. So, this beta u is the weight of the attribute u, right, and the higher the weight for a given cluster, more likely that this the corresponding attribute is a focused attribute. Okay. Then extract focused clusters C that are dense in the graph structure and coherent in heavy focus attributes, okay, and then we detect focused outliers O, that is nodes that deviate from their cluster members with respect to some focused attributes. Okay. So, what are the main components? Inferring attribute weights, beta, extracting focus clusters, then outlier detection. Okay. All right. So, the first task is to infer attribute weights, okay, and how do we do that? So, this is the procedure algorithm that they proposed. Okay. So, what we have as an input the set of exemplar nodes CEX, okay, and what we want to derive? We want to derive beta. Okay. So, now what we do? We define two sets, right. PS is the set of node pairs which are similar. Remember, PS consists of node pairs like XY, right, UV and so on and so forth, which are similar. So, X and Y are similar, U and V are similar and so on and so forth. PS, this S correspond to similar nodes. We also define another set called PD, dissimilar nodes, set of dissimilar nodes. Okay. So, how do we populate this PS set of similar nodes? We take a node from, we take a pair of nodes from CEX, right, U and V, right, and we create a pair UV, and then we add this pair to PS, okay, because we know that within CX all the nodes are similar, okay. So, we take pairs and we basically populate PS. And how do we populate PD? We take all other nodes which are not part of CX, right, and similarly we take pairs, right, and then we populate PD, okay. So, but what we do, we try to we try to create a PD whose size would be much higher than PS, okay. And then what is our objective function? Our objective function is to minimize this quantity, okay. And what is this? So, if I is a feature vector of node I and if j is the feature vector of j, for each pair in PS, okay, we try to minimize this distance because these two nodes are similar, and for each pair of nodes in PD we try to maximize the distance because they are dissimilar, okay, and we try to learn a matrix A. This A is a learnable matrix, right, which basically looks at PS and PD and try to minimize this. This is a very standard Mohl-Anobisch distance measure, okay, between a pair of vectors, right. So, at the end of the day what we will have? We have a matrix A, right, and this matrix A would be a diagonal matrix, right. So, A 1 1 would be, say, let us say A 1 1 is 0.3. So, this is the weight of the first attribute. Similarly, A 2 2 is the weight of the second attribute. You know, weights of the attributes, right. Let us look at the algorithm now, focus algorithm. So, the input is a graph and the set of exemplar nodes. This set of exemplar nodes are used to measure the importance of attributes. So, the first task is to identify the cores, right, the core components using this function find core set, okay. So, in the find core set, right, first we identify this beta. Beta is the weights of the attributes, and then what we do, so we have this graph, right, we also know the attributes of nodes, right, we create another graph on top of this, and this graph will be created based on the similarity of attributes, okay. So, for every node pair ij, right, we measure the weight. This weight is measured by the inverse of the distance, okay. So, this weight is essentially a distance. So, higher the similarity, lower the distance, right. So, this wij will give a weight of the edge between I and j, right. Then what we do? We identify a threshold, right. We only keep those edges whose weights are above the threshold, okay. So, from the original graph now we get you know, nodes which are connected, right, but can have components, right. We have multiple components because we have removed some edges whose weights are less, right. So, we call these components as the core set. So, these components are similar in terms of both the attributes as well as topology. Okay. So, we find such cores, right, and then for every core I, so let us say this is one core, another core, other core, and there are nodes which are not parts of this core. Okay. So, for every core we take all its corresponding nodes, and what we do, we measure the conductance, right. Conductance cut we discussed in the community direction chapter. So, we measure the conductance, you know, by including a node into the core set which is not a part of the core set now, but after inclusion the conductance value may decrease. Remember, lower the conductance, higher the clustering, you know, the cluster likelihood. Okay. So, we add this node and check the conductance. Okay. We keep on adding such nodes into the core sets and see whether the conductance value decreases or not. Okay. And we keep on adding until unless we see the conductance value starts increasing. We can also use modularity, for example, right. So, this expand procedure, right, I am not going into the details, but the expand procedure basically expands different components, right, by adding potential nodes which are not part of the core components, but after addition the quality of the this community gets increased, right. Similarly, once we expand individual components, the next part would be, it may happen, since this is a greedy algorithm, it may happen that after certain times you realize that you have added some nodes which should not have been added, right. So, what we do, we similarly perform contract. This contraction operation keeps on removing nodes from the cores until unless we see that the conductance value increases. So, it is a greedy approach. So, we need to, you know, repeat this process multiple times to make the communities refined, right. So, through this process what would happen is that there would have some you will find some nodes, right, which would be removed from the core set, right, based on, because core set is defined based on both the topology and attributes, but with respect to only the topology those nodes will be there, but with respect to both topology and attributes those nodes will be removed. Okay. And we call these nodes as BSN. So, BSN is a superset. From this BSN, right, based structural nodes, BSN based structural nodes. Among the BSN set there are some nodes which are also similar attribute wise. So, they would be included in the core set, right, but those which would remain after the iteration in the BSN set, those would be the outliers. Okay. So, this is all about focus co-algorithm. So, we start off with a set of exemplar nodes, right. We identify the importance of attributes. We then create another graph, meaning weights of edges. Then we identify components, right. Those components are cores. We keep on expanding the cores through expansion and contraction operations, and through the process we are left with some nodes which are structurally similar, but attributes wise different. Okay, and those nodes are called as outliers. Okay. So, this is focus core. We stop here, and this is basically about a community centric outlier detection. So, we stop here. In the next lecture we will discuss the relational learning algorithms, and we will also look at dynamic algorithms, dynamic graphs and outlier detection from dynamic graphs. Okay. Thank you.